Okay, so Unit 5, starting out a new unit. Lesson number 1. We want to be able to evaluate expressions with rational exponents. And of course, if you think about a rational number, right, those are the numbers we can write as a fraction. So there's both a numerator and a denominator. And so when we talk about the denominator, we'll be taking a root. If we talk about the numerator, we'll be working with a power. And so that's why we call these powers and roots. And of course, I'm kind of old school. We didn't have these Marvel Cinematic Universes with these very lifelike movies we can go watch. So I'm old school. So that's why we got Underdog going past here. By the way, the creator of Underdog, Jay Ward, same person that did Super Chicken, same person that did Bullwinkle and Rocky, among others. And so here comes Underdog flying to our rescue. Okay, so let's talk about the roots first. All right, we can either write them as an exponent or as a radical. All right, so we're looking at, let's say 25, and I want to see it as a for exponent. I can put 25 to the 1/2 power. Or if I wanted to see it as a radical, right? You probably know that as the square root symbol, although that's really not the best name for it. That is the radical symbol. And here's where it gets a little bit crazy, is that you've always thought of that symbol as just being for square roots. And yeah, it's those lazy mathematicians. There really should be a little tiny 2 as an indus, right? So 25 to the 1/2 power should be the second root of 25, but we get lazy. We just call them square roots. With any other root, we actually show the indus, right? We're just too lazy in that too. So if you want the cube root of 8, you say, hey, 8 to the 1/3 power would be the third root of 8, or the cube root of 8. Right? If I wanted 81 to the 1/4 power, that'd be the fourth root of 81, right? So that's not a square root symbol, that's a radical symbol. And the little indus tells us how many times we need to take the root. So how do we find these things? Well, here are those 3 examples we just saw a moment ago. 25 to the 1/2, 8 to the 1/3, 81 to the 1/4 power. Well, 25, of course, is 5 times 5. And that exponent tells me I want one of those 2 equal factors. So I just want a 5. 8 to the 1/3, well, 8 is 2 times 2 times 2. And the exponent says I want one of those 3 equal factors. Notice I didn't do 4 times 2 for 8. 4 times 2, that only give me 2 factors, and they're not the same number. I needed 2 times 2 times 2 because I needed 3 factors. That's what the 3 in the denominator is telling me. And they had to be identical. So when I want to do 81 to the 1/4, I know a lot of you are thinking, hey, how about 9 times 9 for 81? That doesn't get me 4 equal factors. I need 3 times 3 times 3 times 3. I need 4 equal factors so I can take one of them. All right? I did not use 9 times 9. If I wanted the second root of 81, then I could have done 9 times 9. But if I wanted the fourth root, I had to use the number 3 4 times. All right? 4 equal factors to take a fourth root. Okay, now evaluating versus solving. If I give you an expression, you can evaluate it. So if I say, hey, take a look at this, and you say, oh, that's easy, square root of 25. There's just one answer, it's 5, piece of cake. If I ask you to evaluate, negative square root of 25, piece of cake, there's just one answer. It's negative 5. The difference is when we solve an equation and I have something like x squared equals 25, I don't know what that crazy variable x is thinking. I don't know if it's thinking 5 times 5. I don't know if it's thinking -5 times -5. So when I want to undo that exponent and I got to take the square root, there's actually two answers, a +5 and a -5. So notice besides putting the square root symbol there, or the radical symbols I should be saying, I had to put a plus or minus in front. So either -5 or +5 would be a solution. Okay, powers. Dun, dun, dun. Again, we can write them as an exponent or a whole bunch of multiplication. Right? I can either write this as 2 to the 4th, that's with an exponent, or I could write 2 times 2 times 2 times 2, right? A bunch of multiplication. And if I want to evaluate an expression, well, right, there's 2 to the 4th power. I have to actually multiply all those 2's together. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. There's my answer. If I wanted to evaluate -2 to the 4th power, piece of cake. I've got -2 times 2 times 2 times 2, which is a -16. Notice the negative symbol just sits there. Big difference. I'll show you in a moment with a big difference. Sometimes it helps if you think of that as being like -1 times 2 to the 4th. Then it's more clear because you're like, hey, 2 to the 4th is 16. So I've got -1 times 16. That might make it more clear why it's -16. The big difference is when the negative is inside a set of parentheses with the 2. This is when each factor is actually a -2. If I multiply the first two factors together, I get a +4. But now 4 times -2 comes out as -8. -8 times -2 comes out as a +16. So notice the difference. If I just have a negative symbol out in front with a 2 to the 4th power, the answer will be -16. But if the negative is inside parentheses with the 2, notice that I'm alternating between positive and negative depending on how many times I'm multiplying. If the negative is inside the parentheses and there is an even power, it'll come out positive. If it's inside the parentheses and there's an odd power, it'll come out negative. Okay, so now we're getting into the really good, interesting stuff. All right, let's pretend I'm looking at 512 to the 2/3 power, and I want to evaluate this without touching a calculator. Well, I want to first take the root and then raise it to the power. I could do the other order, but if I take 512 and raise it to the second power, I'm going to get a really, really large number to work with. So instead, I'm like, no, let's take the third root of 512. Right? We'll do the root first, shrink this number down, and then we can raise it to the power of 2. So if I'm looking at 512, I'm like, well, that's 8 times 8 times 8. Right? So if I want the third root, I just want one of those 8's. Notice on the exponent, I only have the 2 now, right? We've used the denominator of 3. I don't need that anymore. So now I've just got 8 squared. Well, that'll be 8 times 8. That'll be 64. Something you might notice that 64 is less than 512, right? That exponent of 2/3 told me I was going to get a result smaller than 512 because 2/3 is less than 1. So I knew that my answer was going to be less than 512. Also make a note that while it was less than 1, it's also greater than 0. All right. And of course, I ended up using 2 of those 3 equal factors. That's what that exponent of 2/3 is telling me. use 3 equal factors to make the 512, use 2 of them to make that 64. And if you're in the classroom, I'm going to actually write this on the whiteboard because we're going to refer back to this example in just a few moments. Okay, how about 32 to the 7/5 power? Again, take the root first, the 5th root of 32. So I need 5 identical numbers that multiply to be 32. And so that, of course, is going to be the number 2, right? If I have 5 2s and I multiply them together, they have a value of 32. So the 5th root would just be plain old 2. So now I've got 2 to the 7th power. I can multiply that out, right? The factor 2, I need 7 of them. That multiplies out to be 128. Right? If I did the power first, I'd have to do 32 to the 7th power. That would be a very large, cumbersome number to deal with. And then trying to figure out the 5th root of that very large number would be very difficult. Also notice that our answer of 128 is larger than the original base of 32. That's because the exponent 7/5 is greater than 1. If the exponent is greater than 1, our answer will be larger than the root we started with. If the exponent is less than 1, but greater than 0, our result will be less than the root we started with. I'm sorry, the base we started with. And of course, this is kind of weird to think about it, but we ended up using 7 of the 5 equal factors. Right, the denominator on that exponent, the bottom of that exponent says, hey, you need 5 equal factors. The numerator or top of that exponent says, hey, you need 7 of them. And if you're in the classroom, this would also be going up on the whiteboard because we're going to take a look at these 2 examples. Because I'm sure at this point, some of us are like, oh yeah, piece of cake, I can do that in my head. And some of us are like, you're losing me, right? So if you're thinking, you're losing me, there's no way I'm going to do this in my head, let's go meet somebody that's friendly. Look at this. It's not a multiplication table. It's an exponential table. I've got bases on the left-hand column, and I've got exponents on the top row. So if we looked over at the whiteboard, we'd say, hey, 512 to the 2/3 power is one of the ones we did, and we already know the answer is 64. Right? If we look at the whiteboard, we say, hey, look, we know the answer is 64. How on earth can we get that? Well, if I locate 512 on this table and say, oh, the exponent is 2/3, so look at the 2 and look at the 3. Well, what's going to line up? 64. If I took the cube root of 512, I would have an 8. If I square 8, I get 64. So 512 to the 2/3 is 64. The other example that I would have written on the whiteboard, we already know that the answer is 128. Let's see how this plays out. Locate the 32. The exponent is 7/5. So locate the 7 and the 5. And the answer, of course, is 128. Right? If I took the 5th root of 32, the answer would have been 2. 2 raised to the 7th power is 128. So as much as possible, we do want to do this by hand, showing step-by-step work. But for those of us that mentally cannot just manipulate the numbers in our head and say, well, hey, the 5th root of 32 must be 2, this table gives you an excellent way of looking and say, oh, if I got 32 and I want the 5th root, I must be talking about the number 2, so let me write down 5 of those 2's. And then when we raise it to the 7th power, you can write down 7 of those 2's. Now, I want to do another example because one of the traps on this table, I got to locate a 64. So I located 64. Exponent is 5, 6, so I need to locate the 5 and the 6. And I can declare, hey, the answer must be 32. Notice which 64 I selected, and here's the little trap we can fall into. There are a bunch of 64s, right? 8 times 8 makes 64. 4 times 4 times 4 makes 64. 2 times 2 times 2 times 2 times 2 times 2 makes 64, right? 64 is a perfect square. It's 8 squared. 64 is a perfect cube, right? It's 4 cubed. And 64 is also a perfect 6 power. 2 to the 6th power is 64. So when I want to find the number that's the base, I got to make sure the base lines up with the exponents I need to work with, right? So when I selected at 64, I had to make sure that 64 was lined up underneath the 6 because I had to take the 6th root, right? 64 to the 1/2 would have gotten me an 8. 64 to the 1/3 would have got me a 4, right? There are a lot of 64s. And that's not the only number that repeats. And if this table was much larger and went out much further, we would find there's even more numbers that repeat. Right? And of course, 64 to the 1/6 power gets me a 2. That's why I had to make sure that I picked the 64 that lined up with the 6, because I had to take the 6th root. Okay. Let's assume that for a second you've really tried to work through this. Or maybe you've worked through it and you want to check your answer. Okay, we have things called calculators. You can use a calculator. Hey, those weird symbols on that introductory slide. One of my favorite homonyms, the word carrot, right? There's 4 different spellings of carrot. There's the carrot, that's the vegetable that you eat. There's the carrot that defines the purity of gold. There's the carrot that measures the mass of a diamond. And then, of course, there's the caret symbol, which is used in punctuation. And for whatever reason, a lot of mathematicians use it to let us know that we're working with an exponent. So a lot of calculators have that caret button. Now, I got to be very careful. Notice that there are some parentheses on the exponent, right? If I did not put the parentheses on that exponent, the calculator would have done 512 to the 2nd power, gotten a rather large number, and then taken that large number and divided it by 3, right? If I wanted to actually raise it to the 2/3 power, I have to have the 2/3 inside parentheses to get the correct answer. And then some calculators, instead of using a caret symbol, they've got a button that looks like x to the y power. And so the first number you type in, the x would be the base. And then the second number you type in will be the exponent. And notice, even on this calculator, I had to put the 2/3 exponent inside parentheses. Problem with calculators is they're always going to spit out an answer, right? If possible, try use a calculator where you can actually see what you entered as well as the answer. I believe the calculator that I have on the right-hand side here is the built-in one that's on my laptop. The other one is obviously a TI-84, but I was able to download an emulator for that. Oh, coming to our rescue, flying across the skyline of Seattle. It's Underdog. All right, so it's time to practice using a wonderful little worksheet. There's Underdog.